name NuScale plant and gasgate design. NuScale come to us, request we do some research on sealing technology for their reactor pressure vessel. Just so I can give you a bit of background, NuScale was formed small model NuScale reactor. One of their models is coupled which is 50 electrical megawatts. Their nuclear plants are mostly used in remote areas or can be transported to locations.
NuScale wants us to do some researching about the reactor pressure vessel sealing technology and to choose for them the best one that is on the market for their reactor pressure vessel. They want us to provide them the seal size to prevent leaking, the expected life of the gasket per cycle, the observed spring back, as well as a recommended vendor so they can obtain their gasket from.
This was going to be a plan of action for the semester. The first thing we did, we met with the clients, we learned a bit more about the project, about NuScale, the company, as well as what they wanted us to produce. They were able to give us some specifications as well as some drawings of their nuclear reactor design. Next, we moved into the research phase. After research first, we did some design and modeling, and then we created a report with some data tables for them and delivered the results. So when we met with the client was able to give us a specification showing some operating temperatures, some normal operating pressures as well, and accidental operating temperatures and operating pressures to begin with. This is 2000 and 2200 over here on the right side, and then with that, we also managed to obtain this sketch. This is a sketch that Gary Child that we're working with, who works for NuScale, provided to us. What you are seeing here is a cross section of two flanges bolted together. The bolt is right there in the middle where the white space is, with two nuts on the top and the bottom. On the left side there is the actual reactor pressure vessel wall. The gaskets actually are in two groups on the top flange, and they go around the flange connection. And then this is all we had was that spec and this flange design. The reason why they didn't give us anything specific to the actual dimensions of the flange was because everything they were doing was also still theoretical, and they had not actually built the flanges yet. So we had to reconstruct the flange design, and this is where we went into our research phase. So to begin off, to get the flange dimensions and to start designing and modeling the flange, we looked into SME boiler pressure vessel codes because that's the standard that NuScale does use for their nuclear reactors. Those are the standards mainly used when it comes to pressure vessels here in the United States. And we focused on Section 8, Division 1, and that addresses pressure vessels typically from pressures of 15 to 10,000 psi. This is not, however, a limit. The section can go up to big and higher, but that's what we focus on. And then we also looked at SME B16.5. I'm sorry if this cut off, I'm not sure why. Pipe flanges and flange fittings. We used this codes and standards in order to obtain our pressure and temperature ratings for our design. We looked. It also gave us information on materials that we could utilize. It gave us the dimensions that we needed in order to start modeling our flange and gasket design. It gave us the tolerances as well as the testing procedures and testing the Along with it, these are some of the tables, an example of one of the tables that we're able to use in order to obtain the actual flange dimensions. What NuScale did was they provided to us, all they had for us was an inside diameter of what they thought the flange design would be. So we had to derive everything from there using the B16.5 SNE code. And then we looked at the next table here, shows you where we obtain our gasket outside dimensions as well for the design using what NuScale gave us, the inside diameter. And as you can see, most of these tables only really went up to around 12 inches when it came to design and specifications. Our design was actually 52 inches is what NuScale gave us as inside diameter. So we had to scale everything up. So one of the biggest challenges was to actually understand how these tables came about. And then, so we had to actually go back and scale everything to the larger diameters that we required. We also looked at the next table here, shows you the bolt standards from B16.5 as well. We use this table in order to get the right amount of bolt holes that we needed in order to put our flanges, our two flanges together, and ended up being 32 bolts. Again, that was scaled from this table. And then we go on to the next one.
One of the things that NuScale was concerned with was the expected life of a gasket. Now, fatigue is usually not one of the things that they're concerned with, but they are concerned with creep, because creep comes into play with cracks with the gasket. Some of the materials that we used when testing for different gaskets were carbon steel, silver, and titanium. The reason that we chose these materials was because carbon steel would be maybe not be the best choice, but if it fits the bill, then it's more cost effective. But we also chose titanium because that would probably be a much better choice, but it would be much more expensive.
Springback. Springback is the tendency for material to return to its original after stresses have been applied. This data can only be obtained during tension and compression testing and comparison of material without a known analysis testing produce of our specific material to be used or the gasket.
We contacted 5 companies that are currently in the field to get some information about the gasket. We contacted Metallic, Godlock, Acrylics, James Walker, and Flowserve. This table is summarizing what we obtained from the vendors. We obtained the surface finish, the recommended surface finish of the plant, the recommended surface finish of the gasket, the spring back, the potential leak rate, and the cost. As shows here, for the spring back, the best company that gives us a good information is the Acrylics. They use a particular gasket called photograph. The spring back of this particular gasket is 50% of the original height. For the potential leak rate, we didn't get that much information, but for the company Garlock, they use some testing with nitrogen and for the gasket, and they didn't have any leak sign. For the cost, as shown here, Metallic, which is the #1 company in the market, gives us the cheapest price for the standard gasket. It's around starting from $5 to $2,000, depending on the size and the theater.
Okay, at this stage of analysis, my team and I had an agreement with Mr. Chow, who is our client from NuScale Power, that we don't need to build the project physically, and instead we can model the bars in SolidWorks and run the theoretical analysis in as for 2 different reasons. The first one, that we can't build the project physically because we have very large diameter of the flange and the gasket. And the second one was we cannot obtain the data that's given from NuScale about the pressure and temperature. For SolidWorks, the first step in SolidWorks, we talked to Mr. Chow to get parts information like dimensions and the sketch that represents the flange. And then we defined the dimensions based on ASB codes. After that, we built the parts in SolidWorks and then assembled each model with different material gasket. And at the end of SolidWorks stage, we send all the models to Mr. Chow to get information about our work. This picture shows the bars included in our project. So there are two flanges and a seal in between, and the two flanges are bolted with 32 bolts and 64 nuts. Here's a short animation shows how did we assemble the bars together. Okay, on ANSYS, the first step was to import all the model to ANSYS, then define the materials. One problem we had with ANSYS that ANSYS doesn't provide any properties about carbon steel, so we had to talk about with Mr. Chow to get the physical and mechanical properties for carbon steel, and we defined those properties in ANSYS manually. After that, we set up all the analysis conditions, and they are basically a structural analysis and thermal analysis, and then run the analysis to get the result. This two picture shows, this one on the left shows the pressure load acting on the gasket in between the two flanges, and we have an example here that shows the result coming from ANSYS.
This table is summarizing the result that we get from ANSYS. We applied, we choose three material for the gasket, each material, and we applied the normal operation temperature plus the normal operation pressure to the model and get the maximum deformation, the stress on the plant, the stress on the gasket, and the shear stress. And also we did the same step for the accidental. We add the accidental pressure and the accidental temperature for our model, and we get these values. As a result of these three tables, we found that the stress on the plant does not change because we have just one material, which is carbon steel. However, for the stress on the gasket, it's changing because we use a different material. And as shown here in the slide, the best material we recommended for the NuScale company is titanium because it has the least amount of stress.
Now, one of the things that NuScale was concerned with was how could we find the seal size needed for a leak-tight seal. Unfortunately, after talking with Gary Chow and NuScale, we had figured that the best way to determine it would be to actually build small-scale models and see how it works out. Unfortunately, NuScale did not want us to do small-scale testing, so we were unable to provide this. In addition, some other stuff that they were concerned with was the expected life and temperature and pressure of operation. This we were also unable to provide for NuScale because NuScale was unable to give us some of the material properties that we needed to plug into ANSYS. However, even though we weren't able to do that, we with our ANSYS analysis, any of the missing parts that we need, when we give them our workbench from ANSYS, they're able to plug in those, plug in the data and get the result of the expected life, temperature, and pressure. And lastly, NuScale wanted us to recommend a vendor for them that we thought was the best, and our recommendation was Technetics because they were very helpful with our project and providing us the most useful information out of all the other companies. In addition, we thought that their products were fairly affordable compared to the other vendors in the market, and they had a wide variety of gaskets to choose from.
So just to recap, this project was mostly us just starting off NuScale on the new design, and so everything was very much theoretical. So we just got started on researching some of the certain technology on the market, dimensioning their flange and gasket design, the SAD codes. We 3D modeled it, and then we did some ANSYS analysis of just stresses and stresses using ANSYS, and then we're unable, unfortunately, to obtain them for the life cycle as well as seal size for a leak tight seal, because we use that Chris mentioned life cycle was because we're not actually able to obtain some of the material properties, the seal size, and they have any physical models for us to actually test. And so what we delivered to them to get them started on their next phase of the project was the ANSYS data, which was compiled in those 3 tables that they presented. The spring back data on the gaskets that we managed to obtain from the manufacturers, because we could not do some testing ourselves to actually find data on our own, as well as the 3D models that we applied, so they can utilize this for their next stage when they actually start doing some physical prototyping, some physical design of their reactor pressures. And we'd like to acknowledge here from Gary Shaw from NuScale, who was our client and our sponsor, Dr. Thomas Cooper, our advisor, Dr. Suresh Dash, and Claudio Propana for helping us with the theory behind the life cycles, as well as SolidWorks and the ANSYS analysis. Any questions?
So you got the spring that allow properties of the seals from the vendor, and you calculated the gap. Were you able to draw any conclusions of based on the gap allowable of what would be the best choice for a seal?
Well, I was just going to say that it varies a lot from our research that we determined. Basically, one of the things that it comes down to, and there's a lot of different factors. When we were talking to the vendors, the main thing they were concerned with was the flange finish, and if depending upon the flange finish, that's what helped determine the spring back. Well, not necessarily the spring back, but like the seal size and everything. So
without that, without NuScale giving us any more data on their flange, because they have not even done the actual final design of them, or they have not built any physical flanges themselves, so we could not have any data for us to derive exactly what would happen to the seal once it's in the flange. So we just used the flange that we modeled using the SME code for scan.
So the spring back from the vendor was a function of surface finish.
Yeah, it was a functional surface finish, and then they, for example, was one of the vendors, after the actual name, I can't recall, gave us a surface finish on their gasket of 50% based on their testing procedures, based on the flanges that they used that one. It was Gallup. Technetics was the one that gave us, because one of their gaskets had a 50% spring back to its original size after the compressed.
Was that one of the ones that you measured a large amount of spring back or a small amount in your analytical model? Did it correlate well?
We didn't actually measure the spring back with our analytical model.
Well, you mentioned you have a gap, right? That you measured in your model, a deflection, you called it?
Yeah, we did that, but we were unable to do the spring back in ANSYS.
I had a question. What was that deflection that you had? Where was that? You had a deflection you're showing the tables of half an inch. I was just trying to understand where that deflection was. And max deformation is 0.5 inches. The max deformation. What is that? The deformation of the seal? Or is that
Yeah, that was the definition of security.
Because the pressure was acting normally on the seat.
okay?
And between the two lines.
And so is the final question, is it supposed to seal with that half an inch of deflection? Is that what, I missed that.
The whole, this is but just the data of just applying the forces on it to find the definition. NuScale actually wanted us to find the actual definition that would be required for sealing. And then so when we talked to our professors, when we talked with Gary, we realized the only way we can truly test that is if we have all the data on the surface finishes of the flanges. And then we would actually build a physical model and test it and see how much deflection we have, and then find the maximum deflection. So we're not able to obtain that at this stage. That would be the next step.